This is the third part, the third lecture of our engineering basics lectures seminar. What was it that the workshop there? I like that word. So we're going to call it the engineering basics workshop. So today we're probably going to be finishing up statics basics. There is more covered like in the statics class, and some of it we'll touch on later. But today we're going to hopefully finish with statics, which means next week we'll actually start looking into some 204, 207 stuff. All right, so today we're going to be talking about 3D static equilibrium, distributed loads, and friction. So just as a refresher, this was the problem that we didn't get to last time. This example, we had a 300-pound reaction on the... can you guys see the mouse?
Yeah.
Okay. We had a 300-pound reaction down here. And then a 450-pound pedal force, so that means the force coming from the brakes is 450 pounds. And we were asking how hard can the driver push and what angle do we need to stop at? Now I'm not going to go over the whole explanation today, just for the sake of time. But it actually ended up stumping me for a while. This is an interesting problem, so I thought I'd share a little bit. Here's kind of the Freebody diagram that we recognized. Now, the issue with this Freebody diagram is that we actually we constrained too many things. So there was an assumption that we made that this force here was remained perpendicular to the pedal. And actually, given our loading conditions, that's not possible. I actually ended up solving this, reworking it over 2 or 3 times, and I kept getting down to the bottom and saying, wow, the sums of all 3 of my defining equations are not working. And the issue was that I'd assumed that the angle on here, so we had basically 2 unknowns. We had one unknown that was this angle, theta, and one unknown that was the magnitude of this force. Let's call it F of P, which is what we said. How hard can the driver push and what angle do we need to stop the pedal at? So I thought that, oh yeah, there's only two things we're looking for. That must mean that there's only 2 unknowns. Actually, we have 3 unknowns. So there's also an angle here because we don't know what angle this force actually acts at. We assumed for the last problem it was perpendicular, which ended up working out fine, mostly because that's how I designed the problem. But for this problem, it's not true. So we actually have 3 unknowns, which is still okay because we have 3 equations and 3 unknowns, which means we can still solve it using statics without making any other assumptions or needing any other information that we're not given. So I know these pictures are kind of grainy. The camera that I have, unfortunately, is pretty terrible. But hopefully you guys can make out enough on there. Or if you want to look over it again for comparison, you can look at the uploaded slides after we're done here. But this is sort of what your Freebody diagram should look like. This is what I started out with. You can see here where I made the wrong assumption, where I assumed that the angle here was equal to the angle there. I have them both labeled as theta. So doing it this way, you can work out an equation for x, for the forces in the x direction, forces in the y direction. It's actually kind of neat. It gives you 2 equations in terms of an angle and a force, and you can use trig to solve through that. You divide sine by cosine, which gives you the tangent, so you can solve the angle and solve the force that way. The issue is, I can get correct numbers here, but if we go and try and solve the moments, and again, I apologize for the quality, we try and solve for the moments, you realize, oh, those don't add up to 0. It doesn't work. So what I concluded from that was that I drew the force in the wrong direction, which is a valid thing to conclude. If you can solve something with two equations, but then your third equation doesn't agree, often that means that the two equations that you had weren't necessarily linearly independent, meaning like there's more information missing that you didn't take into account. So that would mean that the forces were the force might have been in the negative direction, or your sines and cosines might have happened to work out just because there's like multiple solutions. But that was wrong. So I tried it again, didn't work again. I ended up getting this Freebody diagram. So this is a little more simplified, but you can see we now have multiple unknowns. So we have the angle theta that the pedal itself is oriented in. This angle, I now called it alpha, between basically saying what this force is. Another way to do that would call it Fp sub x and Fp sub y. If you're not as comfortable working with angles, you can just work with x and y. And you can do all your calculations that way and then combine them in the end to get the total magnitude of the force. I just like working with angles because I realize that I have a moment here, and since I do all of my moment calculations, since I need the angle anyway, I just leave it in. So then I ended up running through that again. Interestingly, I get the force and the angle to be the same as I had previously calculated. So that theta that I assumed is now what our alpha is. The only reason it's a negative here is just because I drew it in the other direction, but that part doesn't really matter. So you'll find it interesting is that our solution here, the numbers end up the same, which is one interesting thing with statics is there are ways to do the problem the wrong way but get the right answer. The issue is you're often not getting the complete answer. So even though I said, oh yeah, if I would have said, oh, that's a day, and I wouldn't have checked my work, if I wouldn't have plugged in the last equation, I would never have figured out that there was missing information. So then I plugged it again, solving for theta. And again, because they're angles, you can have multiple solutions where you're essentially like this equation and this equation intersect. That's actually a lot of times if I have like funky sines and cosines, rather than solving it using algebra, I'll just graph it. So I actually just opened up Desmos and graphed this cosine function and then the sine function next to it. And I just took the answers that were here and here. So one answer was that theta is 134 degrees, which would mean that the pedal was like, let's see, it would mean that the pedal was like all the way, no, not even out there. It would be like down here, which, yeah, we know that isn't true. The other way is saying it's minus 45 degrees, which means the pedal's kind of cocked back like this, like shown on there. Which, although I know that isn't true, for the information that we were given for the problem, that makes the most sense. Another thing to note is that for this problem, the information that we took it from, if we go back to the definition here, this 300-pound reaction at 5 degrees above the horizontal came from the FEA that Kyle did. And one conclusion that we can draw from doing this analysis is that the FEA that he did is more than, it's very, very conservative. So this would say that somehow our driver is able to push on the pedal with a force of 3,000 pounds, which we know isn't possible. And it also means that this pedal would have to be at an angle of 45 degrees cocked backwards, which we also know is impossible. So it means that his FEA was conservative and that the aluminum bracket that he made should never fail. But that leads us on to today's topic. Before we jump into this, does anyone have specific questions on this problem? I know I kind of rushed through that explanation. No? All right. We'll continue. All right. So here's what our equations look like in 2 dimensions. As I've kind of teased before, in 2 dimensions, because you don't have that third, you only need to describe forces in each of the dimensions. So we've got a sum in the x, we've got a sum in the y, and then a moment, which means you can rotate in the xy plane. But in a given plane, I'll draw this plane obliquely. In a given plane, right, you can only have one rotation, which is going to be something that's perpendicular to the plane. So this is why we only have one sum of moments we need. But in 3 dimensions, we now have a bunch of equations. So in 3 dimensions, because we have 3 planes, I like my planes in black. So we have an xy plane, a yz plane, and an xz plane. And then, of course, now that we have 3 planes, we have 3 different normals, which means that we have 3 different rotations. So if you're wondering why, oh, well, it makes sense that we add another force. Why do I add 2 moments? Well, the reason is because we've added 2 more degrees of freedom that things can also rotate about. So this is the most complicated that you'll ever need to do in engineering, in statics, and in dynamics. We only live in a 3-dimensional world. If you're ever talking about 4-dimensional rotations or using tensor products, that is for a quantum physics class, and you can join me on Friday mornings. It's pretty cool. It's live streamed. I can send you a link. Yeah. So now that we are in 3 dimensions, I figure what's the best 3-dimensional problem that we have in the car, and that's got to be the suspension. So here's our front suspension design for this year. The graph that you see here is called wheel force transducer data. So a wheel, let's kind of break that apart. So a transducer here, that's just a sensor of something. It's kind of a catch-all word that is meant to just say this is a sensor that calculates something. So you can have a pressure transducer, which, although it doesn't directly measure pressure, it measures pressure by measuring some displacement for a known area and a known force. For wheel force transducers, we actually measure some voltage for a known system that we know is going to react certain ways based on calibration. So if you ever hear, oh, we used a transducer, there always has to be some qualifier in front of it to say what it's measuring. So wheel force transducers for the Baja car basically look like this thing. So it looks like a big funky wheel, and it's really cool. It measures forces and moments in every direction. So you can see on here we've got force in the x, force in the y, force in the z, moment x, moment y, moment z. And then it measures a couple other things, but for our purposes today, we don't really care about those. But this year, the testing that we did this year at Hollister is the first time that we've ever had access to all this data, to this wheel force transducer. So we were actually this year able to design, to do a much better design of the upright. of the front uprights, and really the whole front suspension, because we have some actual real life data from testing. Before, a lot of our analysis was just kind of what we thought it was. And a big part of that is, again, because we're now working in 3 dimensions. And whenever your problem jumps into 3 dimensions, it gets 3 times as complicated, not just twice as complicated. So I thought to explore this topic, we'll try and figure out what our reactions are from one of these wheel force transducer tests. So actually for the front hubs and for the front uprights, we identified several different loading cases that were sort of the worst thing to do. For those of you that aren't familiar, a loading case is just some situation where certain loads happen. So the reason that we chose these loading cases were they were the worst that we observed in different situations. So this one, number 1, happened to have the largest magnitude x direction, force in the x direction. This one in the y. And that doesn't mean that the force in the y was the largest. It just means this is the one where it was the worst. And then we have moment in the y. So that's the moment like rotating about the y-axis. If you can try and picture that in 3 dimensions. If you remember that right-hand rule, if you stick your thumb out, and you curl your fingers around your thumb, that direction that you're pointing is the y-axis, and you're rotating. Then the next one here is the moment. Oh, that should say moment in the z. I think I actually fixed that later. But yeah, the maximum moment in the z direction. So yeah, you can see here that this magnitude is larger than that magnitude. One of the reasons that we do this, that we identify loading cases this way, is that some of the problems that we solve are just extremely complicated. There's no way that we can analytically figure out, okay, what combination of forces and moments is going to be the worst that we think we'll ever see. Now, it's certainly likely that there's something in between these where the force in the x might be a little lower and the force in the y might be a little lower, but together they actually end up being worse. That's part of the reason that we design the safety factor. That's why we do more testing. But for our purposes, this is a pretty good approach to design. So we are going to analyze this 3rd case, the maximum moment in the y direction. And the reason being is that this is the worst loading case that we really identified on those uprights. Now, one caveat I have to say is that we'll be talking about the uprights from last year. So that's these guys. The reason is that all of this loading happened on these uprights. So now going into this year, we can use that data and design around it, which is what we did. There were some geometry things that were changed kind of according to this data. But if we use this year's design with last year's data, then all of our directions are going to be slightly off. So we're going to analyze last year's uprights, which are the ones that the wheel force transducers were on, the ones that we used for testing. All right, so what is the first thing that we need to do for any statics problem? It's the same in 3 dimensions as it is in 2 dimensions. First thing we need to do is actually create a drawing of what's going on. So I took the liberty of going ahead and taking measurements for all these things. So I'm assuming that this load happened when the wheel was at ride height, which means the suspension was sort of in the configuration that it was designed in. Technically speaking, we could see like different loading situations. If, say, the the wheel was turned to the side slightly, or if the suspension were either raised or lowered, right? Because your whole situation is now oriented differently 3 dimensions. But we'll go ahead and make an assumption that this all happened at ride height. That's actually something, if you look on here, the vertical axis and longitudinal axis, this information is how you would remove that assumption and actually be able to use the real data. I didn't have access to that when making this presentation, and I don't think it'll change our results that much. So we're just going to go ahead and make that assumption. So at ride height, which is where everything's designed, which means I can measure it in CAD, the whole upright is actually turned slightly backwards at an angle of 15 degrees. If you look at our car's suspension, at the Baja car suspension, the suspension in the front, actually, it doesn't move straight up and down. It moves at this inclined 15-degree angle. There's some interesting vehicle dynamics reasons as to why we do that. But for now, all we need to know is that in space, this is cocked to the side at an angle of 15 degrees. The other thing we need to know is the distance between where our uprights are. So, or not the uprights, the A-arms. The A-arms, if we go back here, the A-arms, so this thing here and this thing down here, aptly called because they're arms that are shaped like A's. Those are where we will see the reaction forces on the upright. These little balls that are shown here, these are spherical bearings, which means that they transmit a load, but they don't transmit any moments. So they can take a load in any direction. Let me see if I can draw one. So these bearings kind of shaped like this. If you look in cross section, you can use more color stand out. So these bearings are allowed to move freely back and forth, so they can rotate however they want, but they can't move side to side or up and down. This means that if we were to draw that kind of in 3 dimensions, I'm just going to draw it as a sphere. For our purposes, we can pretend it's a sphere. So this means that it can take a reaction force in 3 directions. And what's good about that is it's both good for our design and it's good for our analysis, because this means that when we try and figure out how the system reacts, we can solve this statics problem. Remember, you can only solve a problem with as many unknowns as you have equations. So if we have 3 unknowns for the upper A-arm, for the spherical bearing is part of a rod end. Basically, it's just the name of the piece of hardware that it sits in. But we're trying to find the reaction for the upper A-arm rod end and lower A-arm rod end. And since each of those have 3 unknowns, that's 6 unknowns. And since we're working in 3 dimensions, we have, since we're working in 3 dimensions, we have 6 equations. So let's try and figure out how those separate themselves. So we've got, first of all, I'll try and do as much as I can on here, and hopefully we won't clog things up too much. So I'll draw our measured forces. So this is one direction, and a third direction. And then we've got moments in each of those directions too. So first thing I'm going to do is label our coordinate systems. So this one, actually I'll make that bigger. Oh, not that big. this, oh no, straight line. There we go. We'll call this, I believe on the car. Oh, Daniel, what direction is that? That's the X direction,
right? Pointing out from the spindle?
Yeah.
Yep.
X, yeah, Z is pointing up. And then Y actually points backwards.
I thought Y pointed forward. Right? Wouldn't that make it right-handed? X goes to the right, Y is forward.
Remember, this is the car from 2 years ago, so that one it actually does point backwards.
Isn't that a left-handed coordinate system?
X, Y, Z. No. X, Y, Z. Oh, no, you're right.
Maybe they had Y up 2 years ago or something.
Oh, yeah, that's what it is. Y is up.
That would make sense. Then Z would be backward. Yeah.
Yeah, that's what it was. Oh, yeah, and that's probably why the moment in Y was the worst. That would make sense. Okay. Now we've got our coordinates aligned. X, Y, and Z. And I'll go ahead and label these forces F X, F Y, and F of Z. And then we also have moments. So we'll draw another moment coming out here. So moment in X, moment in Y, moment in Z. If it's weird to think of moments as vectors, just imagine that you're trying to rotate this whole thing with your thumb sticking up. You're trying to rotate the whole thing in that direction. So I'll go back to our slide here. Copy those down really quickly. So that was minus 1773, 4448, 489, 259, and 909, and minus 412. So technically, since we're drawing our free body diagram here, and we know the directions of these forces, it would make sense to actually draw whatever we said has a negative in the negative direction. So, for example, our force in the x direction is minus 1773. So Fx we know equals minus 1773. You could do that. I'm actually going to leave everything positive because since we're working in 3 dimensions, it makes it so much easier to keep clear in your head if you keep everything in the direction that just makes the most sense to be positive and you let negatives carry their way through. Now, this still holds true that, let's say I point something in this direction, right? I point one of my reactions that way, and it actually ends up being negative. That means that whatever direction I drew it in, it will be the opposite of that. So the rule that we had in 2 dimensions does carry forward to 3 dimensions. But I like to draw everything in 3 dimensions, especially my unknowns, in positive directions. It just makes everything a lot easier to think of. So I'll do that next. I'll draw the reactions here. And I can split it up, or I can just draw it in some random way. So I'm just going to draw it like, I'll make a little thing. I'll draw it like that. We'll say it's going that way, and we'll call this reaction pop. All that R E. And then we'll do the same thing for the bottom one. We'll just draw it the same. We'll draw it here, just in some random direction, and we'll call that R, call that RB for R bottom. And this is another good reason that you want to list your knowns and unknowns. So if someone were to just take a look at this, they might say, oh, you only drew one vector for RT and RB. Does that mean that you know what direction the force is? Well, no, we don't. So this is one of the reasons that we want to list our knowns and unknowns. So we'll say knowns are fx, fy, fz, mx, my, oh dear, weird, and mz. And then our unknowns, pop another text box here. Our unknowns, or unks, are RT X, RT Y, RT Z, and RB X, RB Y, RB Z. Another way we could write that would be saying that we don't know R T as a vector. This is another way of saying I don't know, so this is still under my unknowns, I don't know RT, the magnitude, or its direction. Same thing with RB. Let's go ahead and put this here, so space. There. Okay. So now we should have a complete free body diagram. We've put our sketch there. We have our coordinate system. We've put all of our known forces, all of our applied forces, and we've put our reactions on here. Now that we've listed our knowns and unknowns, we can start trying to do our solution. And I left, back on that other slide, I left the dimensions back there. We'll go ahead and collect those now. If you guys want to take a screenshot of that real quick or write them down, they will start to get confusing really quickly. So remember that inclined angle, so that's the angle off of the XZ plane, is 15 degrees. And the X, this is going to be X, Y, and Z distances broken up there, are those that are shown. So 5.724 is the Z direction. We have minus, let's see, X equals minus 0.939, and Y equals 1.534. So if we look back here, using those distances that I just said, note that those are distances from this bottom point down here. And actually, because I know the distances from down there, it will make more sense to put my coordinates, actually my coordinate system, see if I can grab all of them, to put it down by that, we've got most of them, to put it actually centered on that point. That way we can say that this is where we know everything, where we know all of our important dimensions. So now you need to know dimensions to the spindle. So we can assume that the center, the location of the center of these forces is on the y-axis. I believe the wheel force transducers, you can correct for where that was. It might be in the center of the spindle, but we'll go ahead and just make our assumption that that's on the y-axis. Grab all of these. Maybe not. We'll grab all those and put it on the y-axis, but coming through the spindle. Hopefully. There we go. There we go. Okay. Put the F. So the last dimension that we'll need is the distance from the spindle to one of these points. So the distance from the spindle, what I happened to measure was from the spindle to the top one. So this distance here, I'll draw that in black. This distance here, that distance is 4.668. And the distance between the top and the center of this spherical bearing, so this distance here, is 0.717. All right, so now we should have enough information to do all of our calculations. We'll go ahead and duplicate this slide. Add another one there. And we'll give ourselves some more room to work. Okay, so now we'll work on solving. So for all these equations for solving 3D, you do exactly like you do in 2D. So the easy ones we'll start with. So the sum of the forces. So we'll start the sum of the forces in the x direction. Sum of the forces in x equals 0. So we have Fx here. Fx acting in the positive x. Then we have assumed that Rtx and Rbx are in the positive direction. Remember, I just stated that I assumed they were positive, even though they're drawn in some random direction. I'm just saying they're positive. If they happen to be negative, that's okay. So we've got plus Rtx plus Rex equals 0. And we can do the same thing in the y direction. In fact, we can do exactly the same thing. I'm just going to copy this, paste it. We'll just make all of these y's. Y, fxy, and rty, rxy, fy, rty, and rby. There we go. And again, in the z direction. Undo. Ooh, I cannot undo. All right. That's fine. We'll pick that again. Move it down. Okay. So we'll erase these. Okay. These are all in the z. And those equations should all be pretty straightforward to solve. So this is good. E, E, and oh, F or FTZ, RTZ, and RDZ, and of course Y. Okay, so that's the first three taken care of. Those are the easy ones. Now the next ones are going to be a little bit more challenging. We have to identify all the moments. So again, I'll go back here, duplicate the page. We'll move it down so we can, not that far, we can look at it. So now we need to identify the moment. So because it's in three dimensions, now each force can potentially cause a moment in all three directions. So let's just start with the moments about the Z. So we know some of the moments. I'll erase these again so we have some room to work with. So we know that the sum of the moments in the x direction equals 0. That's sum of all the rotations that we could possibly make about the x-axis. So the easy one is, of course, mx, because we're just told it is a pure moment. Pure moments, in 2 dimensions, we drew it kind of as an arrow like that, centered around somewhere. Remember, these are vectors, so a moment is describing a pure rotation in a plane. So we can move it wherever we want. So because that's still true, that means we can move the location of this moment to the origin, and it doesn't cause any force couples. It doesn't cause any other reactions. So we can treat it purely as a moment. So we've got mx. Now we need to add the moments due to RT. So we've got to add the distance to RT rotating anything that'll cause it to rotate this way. So if we break up RT into x, y, and z components here, so that's x, r, e, and RTY, so it's F, R, E, Z. So the one force on here that can't cause a moment in the x direction is actually the x force. So if we go here, remember when you're trying to rotate, this is where the right hand rule really helps. If you take your right hand and you put it on the screen, if you have your force, so your force is the x force, there's no way you can put that force in the x direction so that it can rotate around the x-axis. It would have to do this. You'd never actually be able to turn something. So, go back. There we go. That's drawing right. Okay. So this force, this RTX, we don't have to worry about causing a moment. The other two, however, can. So RTY, if we said, just for example, that RTY was located out here, well, this is now a force separated by a distance, right, that can rotate around the z-axis, or around the x-axis, the axis that we're talking about. Similarly, RTZ can do the same thing. So if it's located down here, and that's now also a force separated by a distance that can rotate around the x-axis. So for each of our reactions, we have to add 2 moments. We'll move this aside, we'll move this down here. So this is going to be plus the distance to RT, I'll just call this dt. And remember, this is from the origin. Distance from the origin in the t direction. So this would be, we'll call it y. So this is the distance to point t in the y direction. So this distance times r e z. So remember, if we have z separated lower, so this is a y dimension that it's separated by. Now this is where RTZ acts. So this is what causes our moment in the x direction. So our distance is in y, our force is acting in z. And together, if you think about the cross products, right? Together they'll cause a moment in the x direction. Does someone have a question? No? Okay. It sounded like someone maybe had a question. Okay, so then we'll add the same thing. So we'll go d dz. Now from the y reaction. So now we're going to separate the y force from the x-axis, separate it by some z distance, and that'll cause a moment in this plane. So that was just for the top reaction. So now we also have to add it for the bottom one. So we've got plus d ey r ez. That's again the y distance to point B, and y distance, or sorry, and the z distance to point B, r b. Okay, and that all is equal to 0. Now, because of where I've chosen to take my moments here, I actually can cancel out these locations, or I can cancel out the reactions from these moments. So our distance at point B, dBz, is 0, right? Because we have we've put our coordinate system at point B down here, right? Put it at point B, which means this is 0, that's 0, and that's 0, but that's 0. The whole thing is equal to 0. Oh, and it looks like I've left off some. So I left off one. Maybe the more astute of you will have noticed. Since we moved our coordinate system from where the force transducers measured, from where the wheel force transducer measured, now we have another moment caused by the z force that the wheel force transducer showed us. So we have this other moment here caused by Fz separated a distance. Now we don't have one from Fy, because Fy is in line, so the distance to Fy would be 0. And we don't have one from Fx, because remember, that's in the same plane. So you can't cause a rotation about the x-axis in the same plane as this x force. So we also need to say plus F D E F. You know what? Let's go ahead and label this coordinate. We'll just call this point A. That point A right there. So call it the distance to A. All right. That was everything for just the moment about x. So we've got to do it 2 more times for the moments about y and the moments about z. So let's go ahead, copy this again, move it down here, and we'll do the same thing. So now we want the sum of the moments in the y direction equals. So we've got my, because remember this is just a vector, we can slide around. Now, since we're acting in the y direction, we have to look, okay, is there a z force that's more than a distance 0 from the y plane? And the answer is no, actually now. So the distance from either fx or fz, since they're located on the y-axis, is 0. So we don't have to worry about any more of those in the y direction. The moments, y moments are now, is this my is all we have to worry about, plus all of the moments due to RT, so that's RE. We'll start with X, so if we have something pointing in the X direction, acting about this point, so it's up here, that means it's going to be rotating like this, right? We're pointing, if we have a force, that, right, is our dx, 90 degrees. We're trying to point that way. Now we have a y distance there, right? Oh no. We're trying to find moments about y. So that's going to be x pointed this way is going to have to be separated by a z distance to rotate around y. Yeah, sorry if that was confusing. We are not rotating in this plane. We're rotating in this plane, right? Because we're rotating around the y-axis. So this is RTX separated by a distance RTZ. Now we do plus RTZ, and you can kind of see the pattern here, separated by a distance RTX, and plus REX separated by a distance in the Z, plus RZ separated by a distance X. That all equals 0. And we can do that same thing one more time in the Z direction, but I'm not going to bother writing it all out because we have more important things to do. So once we do all that, I'll duplicate this one more. Once we do all that, we'll have 6 equations with 6 unknowns. And we can use a handy shortcut. If you find the determinant of a 6x7 matrix, then we can use that to solve all of our equations. This will give us our t, x, y, and z, and our b, x, y, and z. And there's actually, if you guys have a TI-84, there's this function called polysmlt2. So if you go to program, it should be PLYSMLT2. And there's actually a nice interface where you say how many equations you have, how many unknowns you have. And then if you fill everything out neatly, it should give you values for your T reactions and your B reactions. And the way that you kind of fill out this matrix is you put your equations, you have one equation per line. So this would be 6 lines. And then you've got one variable per slot. So we'll say that this is our first slot is RTX, second slot RTY, third slot RTZ, and then the same with RB. So let's see what that would look like for the the first equation here that we had. So for sum of f of x, so we've got f of x plus rtx plus rbx. So if we look in our solution matrix here, we've got 1 times rtx. So we've got a 1 here. 0 times rty, 0 times rtz, plus 1 times rbx, 0 times rby, 0 times rbz, equals, if we go back here, we rewrite this, we'll get 1, right, 1 rtx plus 0, 0, plus 1 rtx equals, you can subtract f of x over minus fx. So if we go back to our solution matrix here, this will be a minus fx. And remember, fx is a constant. It was what? Minus 1,773 pounds. So that's just a number that we plug in there. And you can do that the same for each equation and for each of our unknowns. So every equation that we have, right, is a linear combination of our unknowns plus some constant at the end. So for example, here you'd have, for the moments about x, I'll do this one too. So our coefficient is dty for the reaction at t in the z direction. So we'll say this is the next equation here. The first equation was forces in x, and we'll do moments in x. So this in rtx is a 0, right? Because for our moment equation, we didn't have rtx anywhere. Similarly, we know rbx is a 0, so we didn't have that anywhere. Then let's see, rty, our coefficient is dtz. Remember, this is just a constant from our geometry, so dtz. So rty times dtz and rtz times d dy. And similarly, this is similar for b. So this is d and d ey. If we look back at our equation here, if we move all the constants out to the other side, we'll again end up with just minus mx over here. So we've got minus mx over there. And you can follow that through for the rest of your 6 equations. And if someone wants to plug everything in and maybe tell us the solutions later, that would be swell. But otherwise, maybe I'll post them. Maybe I'll add a slide when I post these publicly with it all solved out. But I think that leaves us, with just enough time to cover our last 2 topics. Before I move on, I know that was a lot to cover about 3D equilibrium. Hopefully I captured all of it in one problem. But before I move on, does anyone have questions? Nobody? Wow, must have done a good job then.
Kind of just vibing over here.
Oh, okay.
Yeah, you
awesome.
did a great job.
Ernesto, did you have a question?
No, I said, yeah, you did a great job.
All right, awesome, cool.
It was a nice refresher.
With that, we'll proceed to distributed loads. So, distributed loads are something that looks really complicated at first, but is actually really simple. So you can think of a distributed load as a bunch of moments that we really want to figure out how we can average them all out. So if we have this triangular load. So what would cause something like this? So let's say we have, we've got a dock here, right? Just a dock. We've got some water, you know, water goes all the way up to the beach. Okay, but this is some dock that's under construction. So we've got a big pile of sand here. And I don't know, let's say there's a wall here that's holding all the sand up. So this sand, the weight of the sand is causing a load on the dock. And the weight of this sand, it's gonna even itself out to where it'll look like a triangle there. And I'll draw that again in black. So the sand will just shape like a triangle. Now you know that the weight of something, right? The weight of something, obviously over here where there's more sand, right? It's gonna weigh a lot more than down at the end here where there's just like, I don't know, 4 or 5 grains. So we represent that with a distributed load. We say we have this total load, and then we describe this equation here, the equation of this curve that describes what the force is at a specific point underneath it. So the area under this curve, or the integral for those of you that are more friendly with calculus, the integral of this area is the total force that the sand here, or whatever your distribution, that's equivalent to the total force that this whole thing is putting on the dock, or on your, whatever your thing. But, you know, integrals are a pain to work with. This is statics. We like things, it's a moment, it's a force separated by a distance. I don't have the time to count up an infinite sum of little forces separated by little distances. So we can figure out how to resolve this distributed load. It's called resolving the load as something else. So we're going to essentially create something that represents, that has the same results in our equations that this distributed load would. And the best way to think about that is you'll have some force whose magnitude is the area under your curve for your distributed load, located at the centroid of that area. So for a triangle's centroid is located at 1/3 from the bottom of its longest leg. So that's why you have L/3. So this whole load, if we combine it all into one thing, we say that this whole load would have the same actions in statics as a force at this location. So that means whatever moments this would cause, let's say we put our coordinate system here, right? That's the y direction. This is the x direction. So we'll say what the total moment that this would cause is equivalent to the total moment that this causes. This is our distance to the centroid. And then the magnitude of that force within that moment is the same thing as the area under this curve. R equals integral of that area. When you see something in a schematic like this, if you see this W0 is usually it's telling you the slope of this line. So this would be like W0 is the rise and the run 1. So W0 would be something in units of pounds per foot, or newtons per meter. Which makes sense, right? If I find the area of this, I'm going to multiply something that's newtons times meters, so that's my height. So the whole area of this is something that's newtons times meters, newton divided by meters times meters. So we've got for this triangular example, right? The total area is going to be W naught in units of newtons per meter times the length, which is in units of meters, divided by 2. Right, it's a triangle. So meters cancel, and I end up just with newtons, which should be the units of force. So there's a couple different ways that you'll see distributed loads. Really, it's just about whatever the curve is. So if you see a uniformly distributed load, those are the easiest. That's just a rectangle. So you take the height, multiply by the length, and the centroid of a rectangle we know is right smack dab in the middle. So this whole uniformly distributed load is equivalent statically to a force, a force here acting at the center. Now, next week when we get into mechanics and materials, it does actually make a difference. So, if I have a thin sheet of paper, right, while a force just located in the middle of my thin sheet of paper, well, this force is going to cause my paper to just crumple like that, right? If I evenly distribute a force across my sheet of paper, it's not going to just crumble. This is why you can have a bridge, right? Or a beam here, as they call it. For a beam, the whole beam supports this load. So it's not like you're trying to shear the beam just right here. You're actually going to bend it. So rather than looking like this V, it's going to be much more gentle. It's going to be kind of shaped like a curve. We'll get into that more next week. But that's basically all distributed loads are. Whenever you're dealing with them, whenever you're trying to solve like statics and stuff for them, they tend to look much more antagonizing than they actually are. All you have to do, calculate an area, calculate a centroid. All right, now we'll do the last thing. Hopefully, yeah, we've run kind of long, but this should be quick because I think hopefully everyone knows about friction from high school. But the way that we use friction in Baja and for most of engineering, the way that you'll use friction is based on the Coulomb-Moore friction definition, which is actually, friction is ridiculously complicated. There are multiple PhDs, hundreds, if not thousands of PhDs that have already happened and are still to come explaining how friction works. But we're engineers. We don't care about particle physics. We don't care about London dispersion forces. All I want to know is how much do I have to push on this thing to get it to move? So friction is pretty simple. All that you're trying to do with friction is separate something that has some force going down on it. So there's two kinds of dry friction. Dry just means that this is for solid objects, not for fluids. So the first type is static friction, which is you have something sitting still and you're trying to move it, but it's not currently moving. So static friction just has this one constant. So you're going to have to keep applying force, and it won't move until you get to some threshold. That threshold is equivalent to this thing here, Fs equals mu sr. So mu s here is just some coefficient that's empirically determined, so something that we measure. R here, or I prefer to call it N, is the normal force. So whatever force is keeping this object and this surface together. Then for kinetic friction, it's the same idea, except your box is sliding. Now, in statics, right, we'll never have kinetic friction. So you never have to worry about mu kr in statics. In statics, you're always talking about mu sr. So if I have, just for completeness, if I have a box that is moving, then if I were to do some dynamics on this, I would say the force of friction down here, the force of friction, is equivalent to this mu k times r. For some things, mu k is different from mu s, so just the constant that we measure is different. For some things, it's the same. One thing to note, though, is when you're trying to cause something to move, the split second it starts moving, right? As soon as you have that force applied, the kinetic the friction force drops down to the kinetic friction. So this isn't moving, now it's moving. That's the second it starts moving, the kinetic friction is going to be reduced. You can kind of think of that like a ratchet, right? Let's see if I can draw a decent ratchet. So if you have like some sawtooth, right? Sawtooth like this. You can think of, or kind of the way that we think of this is you have two surfaces that have sawteeth that are kind of facing away from each other. Now, in order to push these sawteeth apart, right, the friction force is going to try and prevent you from doing it. But as soon as you get them apart, this whole thing, as soon as you slide it up over here, it's going to be really easy to get it to not slide all the way back down. Like, as long as you keep this moving, it'll kind of glide along the tops there. And you can think of that as being like, once you overcome static friction, then you don't have to work as hard to prevent it from slowing back down. But that's hopefully all you need to know about friction until you start to do much more complicated. But that is it. That's all I have for today. This was, we go all the way back to the beginning. This is the third presentation on statics basics. Today we covered 3D equilibrium. We reviewed a little bit of 2D, and then we talked about distributed loads and friction. Next week we'll start talking about mechanics of materials. It's called constitutive theory, and about how we start doing engineering with real things, not just with these fake rigid bodies, these things that we assume aren't going to move themselves. If you guys have any questions, again, I'll stick around. But that's everything I have for today.